Hello and welcome to lesson number 3 of quantum field theory. We are discussing about quantum field theory in the last two lectures. So those who are watching this series must be aware that we talked about quantum field theory part 1, where I've been discussing more about the evolution and history of quantum field theory. From there, we went into quantum field theory part 2, where we discussed about the the renormalization, what are the problems with spontaneous emission, how Schrodinger's equation was unable to describe the spontaneous emission, and thereby we framed into quantum field theory. In the last lecture, we have discussed a little bit about Dirac equation, which is a relativistic way of quantum field theory. However, in this today's lesson, what I'm going to do is that I'm going to take two aspects. First of all, I'm going to show you what exactly is the equation and what exactly is the problem which arose due to the emission problem, spontaneous emission problem. And I'm going to show you something very striking, very unique, which is why we call, in essence, that Schrodinger's equation is a classical equation. And then from there, we will be moving into standard model. So I really don't know. Let us see. I will try to divide the time. However, in this part, I would like to show you few equations. So I'm sorry if you cannot understand my drawing, because I'm not that good in terms of drawing over the internet. So what I'm going to do first is that uh, I'm going to take the classical electrodynamics model, which is specifically based on the point particles, and let us consider that there is a mass. Say, for example, okay, I will take this one, the red one. No, let us take the black one. Okay, so I take a mass which is m, say for example. This is a point mass which I am taking up as m, and I would consider the mass of a charged particle which would be equal to the electromagnetic mass. So I will call it as m sub em. Okay, so the mass of a charged particle should include basically the mass energy in its electrostatic field. And what I'm doing is that I'm assuming a kind of a spherical mass. So I will take the Coulomb's law, and I will assume that the particle is a charged particle and has got a radius, say for example, as r. I'm so sorry, it should be re, right? So what I'm trying to define is that the mass of a charged particle, which it includes the mass energy in its electrostatic, or I mean to say electromagnetic mass, and assuming that the particle is a charged spherical nice shell, so the mass of the electromagnetic field I can consider as m sub em, right? This would be what? This would be obviously equal to the integral of 1/2 of the differential, I would say the energy squared, sorry, the energy squared. And then what I would do, I will take the differential volume, obviously dv. Okay, this is a small d. I mean to say, if you can understand, this is a small v. That is the differential volume I am taking. And then this should be again, sorry, let me pull it up a little bit so that you can see. Yeah. So, and this would be something which would be again equal to, I would say the integral. I would take the integral, and I would take the mass, this one, this radius, right? This radius, which would be re. Let me write it such a way that you can understand, right? It would be re, and this would go up to obviously infinity. And this would be how much? Obviously, this would be 1/2 of, I will take the Coulomb's law. So obviously, it would be Q by 4 pi r squared. And I would obviously square it. So this would be the square, followed by the 4 pi r square. I hope you can understand the derivation. This is quite simple. I'm not going to explain it again. Followed by dr, followed by dr. Right. So what I'm trying to do is that I'm trying to take the mass of the charged particle followed by the differential volume. I'm taking the mass, which is Re, and I'm taking the simple Coulomb's law to draw it as dr. And when I pull it up across, then what it would happen, this would be something which would be again equal to the charge squared followed by the 8 pi RE. Obviously, it would be 8 pi RE. Now, the basic idea why I'm showing you all this is there is a reason. I will just tell you. Pick up a kind of a different color. Now, what I'm trying to tell is that the energy which is associated with the electric field, that is this one, right? So if this RE is going towards zero, if this RE is going towards zero, this implies actually what? This implies that the point particle would have infinite inertia. This would have infinite, it's a little bit getting clumsy. I would have a pen tab soon and this would be much better. So this would have an infinite inertia, right? So this one, the RE would be the, what is that RE? There's a spherical shell of the radius. This would be going towards, I would say, infinity, as you can understand. The inertia of this cannot be accelerated. So what will happen incidentally is that this RE that makes this mass, where is that mass? MEM, this mass, okay, which makes up this mass along with this radius, which takes up this radius. So what would happen is that it would be equal to the electron's mass, which we would call it as a, I would say, classical electron mass. And what it would be, what would be this RE? Let us see that. Let us, I would to say, let us find out in a very basic way. So this RE, right, would be equal to what? It would be equal to E square. And if I remember correctly, this would be 4 pi, this with the permeability of free space, epsilon naught, followed by ME, which would be definitely the mass that we are encountering, ME, followed by the velocity of light, c squared. And this would be somehow, this would be proportional, this would be somehow proportional to the reduced Planck's constant, that is the h bar, followed by the mass that we are taking, ME, followed by c. And this would be, I would say, approximately equal to 2.7, or maybe, I'm sorry, it would be something around 2.8 times 10 to the power minus something. You need to find out m, right? And in this case, what would happen is that this m, right, this, I'm so sorry, yeah, this proportionality constant that I'm drawing, this one, this proportionality constant, let us take it black again. So this would be somehow proportional to 1 upon 136 or 137, I would say 137, and which is called the fine structure constant, all right? This would be the fine structure constant. This would be the fine structure constant. This would be the fine structure constant. And the h bar upon it would be basically the reduced Compton wavelength, right? So the basic idea, what I'm trying to tell over this equation is that what we have done over here is that we have just taken a small kind of a mass, m, and we have taken the electrostatic field of that mass, and we have found out that this particular radius, this one, let me now draw it in red, this one, if it is tending and going towards zero, this implies that the point particle would have an infinite inertia and hence it cannot be accelerated. So the basic idea of showing you all these calculations, etc., is basically to make you understand that why we are actually, taking these things into account, and how we will be proceeding, because this is a nice kinds of calculation which actually shows how it would go to infinity and what would be the problem. Okay, so now what I'm going to do is that I would be definitely talking about the standard model today, that is basic agenda. But before that, what I would like to show you is that the reason that Paul Dirac calculated the relativistic Schrodinger equation, because it was classical in nature, right? We call it as a classical in nature, and Paul Dirac made it as a Dirac equation, which is the relativistic Schrodinger equation. We have seen that in the last lecture. If you have missed it, you can go there. I've already created a playlist for the first two lectures. Now, if Paul Dirac would have created a relativistic equation of the Schrodinger equation, which was generally classical in nature, can we see mathematically that why Schrodinger equation is considered to be classical? I'm going to say, I will like to show you a kind of a derivation. I won't say it is derivation. It is just a kind of a simple mathematical tool which will make you understand about the classical nature of Schrodinger equation. Now, because I'm writing it over mouse, so all these equations, initially I have written it in LaTeX. So I'm going to share my Sideboard again with you. And with that Sideboard, I'm going to plug and play these equations so that you can literally understand and see. So these equations will become easier. Now, you see that what we would do initially is that we will start with the concept that temperature field exists everywhere in the universe. I will start with the classical notion. Now, temperature field exists everywhere means in deep space, in galaxies, tiny particles, I mean to say, they have a temperature, right? And this field eventually will move in random directions and with equal probability and various speeds. So obviously what is going to happen, let us consider a kind of a space where there are little dotted particles which are moving in a random nature. I'm not coming to the quantum mechanical part, remember. What I'm trying to tell is that these particles are moving in a random motion. So the average energy of a particle, if I consider the mass temperature to be T, so the molecules of our gas, it is in constant motion. So what I'm going to do is that I'm going to plug in this equation so that these becomes easy for you. Let me share the Sideboard once more. Yeah. So you see, I am going to first plug in with this equation. Okay. So here you can see that what I have done, I purely drawn it in LaTeX. So I mean to say, this is very clear and you would be able to understand it very clearly. So what is happening is that this K, obviously, let me take the pointer, let it be the blue one. Yeah. So as you know, this K is the Boltzmann constant. No problem is that. The V square, this V square, I would say, as you know, this is the, we call the root mean square. So if this is the root mean square, I would mention it as RMS, root mean square, say for example, just making some acronyms with it. So RMS is the root mean square. So the square root of V square, I can take it as something as V square to the power 1/2, something like this, right? So that means that this is the root mean square we know, which is actually close to, I would say, the most probable speed at the same room temperature. Now, say for example, if I take this V sub RMS, if I take V sub RMS, right? So V sub RMS is what? The RMS is the speed of the particle. And this equation which you have written actually shows that the RMS, that's the root mean squared speed of the particle, is actually proportional to the square root of the temperature and inversely proportional to this one, this T, which I have taken as the temperature. Okay. Now, say for example, at a given temperature, let us assume any kind of a given temperature, right? At a given temperature, the speed, this VRMS, this speed, what is going to happen is that of lighter particles is faster, obviously, than that of heavier particles. So if I take the de Broglie length, for example, of 20 degrees centigrade, right? This is, I'm so sorry, it is taking a little bit time for me to write. So this is the de Broglie wavelength, right? I'm just writing it as this de Broglie wavelengths at 20 degrees C. So if I want to see that what is the root mean squared speed of electrons, say for example at a room temperature, then what I'm going to see is this one, right? So just I have taken it from a book. So this is actually what tells that at room temperature, the electron speed is how much? 1.15 multiplied 10 to the power 5 ms, approaching 1,000th of the speed of light. This is what we can tell. Now, I believe till now everything is quite clear. and things are proceeding nice and fine. So what we have taken till now, let us imagine we have just taken this equation. We have taken the root mean square at 20 degrees centigrade. We have taken the electron's mass to be something like this, 10 to the power minus 4. Okay, so far so good. Okay, now what I will do, going to do is that I'm going to take the wave, I would say the wave function. Say for example, I take the psi, sorry, this would be of x comma t, right? So we use this psi x comma t just to represent the one dimension electron distribution function. Remember, we are taking one dimension because our basic objective in this case is to show that how the Schrodinger's equation is a kind of a essence of a classical nature. So we use psi xt, clear, that to represent the one dimension electron distribution function. That means at a particular time when the coordinate interval are say x1 to x2, say for example, if I draw this kind of a function, so if I make the coordinate interval from x1 to x2, right? I make the interval from x1 to x2. So this distribution function, I'm going to say this one, this distribution function looks like a standing wave which is fixed at both the end of the string. So if I take this as a string, this would be a kind of a standing wave, right? Taking this one, let me take a different color to make you understand this one, right? So if I take, remember what I'm doing is that at a particular time, at a position distribution function psi x comma t would be actually the distribution function that looks like a standing wave which is stuck at one end of the string. It is just standing. Now the important function of this particular wave function, that is psi x comma t, is that the complete wave function psi x comma t can be written as the product of two terms, and we will see that how it is. One of them depends on x and the other of them depends on y. So one of them will depend on x, other of them will depend on y. So let me plug in the next particular equation over here, this one. Okay, now let us have an observation. So what I have done is that I have simply written the exponential with this traditional wave function, right? So I have written this one, psi x comma t, which is equal to the exponential with the standard. I have just taken the product. I hope you understand. So what is the important function of this equation again is that I'm going step by step slowly. So this is the complete wave function psi x comma t, which can be written as a product of two terms. One depends on this x and other depends on this y. Okay, now what I'm going to do is that I'm going to take the classical physics for traveling waves along the x-axis. Say for example, if this is the x-axis. So I'm going to take what is called the traveling waves along the x-axis, and I will use obviously the partial differentials, and the equation would look like this. Let me put it below this, right? Make it a little bit smaller, right? This would be better. So sorry. Yeah. So it looks like this. Okay. So this is what? This is basically the classical physics, the classical equation along the x-axis for general form of a wave equation. Okay. Let me now define it a little bit, what this equation is all about. As you can see, this one is the what? This is the wave, I mean to say speed of the wave. Now what I will do is that if I substitute this equation, okay, with the equation with this one, I'm just substituting this wave function equation into this equation. So what I'm going to do is that I'm going to substitute this equation over here. Simply, I'm going to substitute this equation over here. And what I'm going to do, I'm obviously not going to do this calculation right now because it is all written in LaTeX. It is easy. Writing over there is a big problem. So it leads to this. Okay. So I just substituted this equation into the other equation. And what I get, and then obviously I divided it by this one. I divided this by this one. And what I get is this one. Now this equation, you see, this equation only contains the variable, sorry, which is the x1, right? So if v is the speed, and if we substitute this equation into the other, and then we divide both sides by this one, this particular part, then what we get is this equation, right? What we get is this equation. Okay, further what we are trying to do is that we know with Einstein's hypothesis, that is the energy momentum, we know that, now let me write these small parts, not written it, that would be E obviously will be equal to h bar omega. Obviously we know this, right? And we also know that P is equal to h upon lambda. This is something we already know, right? So from here, let us once more recall that there are two variables, then we substituted this and we got only one variable, and now we are taking this equation. Okay. Now, since the energy and the momentum of a photon, I would say, originated actually from the transition of an electron from a higher energy to the lower energy, so the transition must satisfy both the law of conservation of energy and the law of conservation of momentum. Because it originated, remember, if I take a kind of an energy state here and here, then it originated actually from here and it actually came back to here. So if I take this one as higher, this one would be the lower one. Okay. So because the energy and momentum of that particular photon, if I consider this to be a photon, this one, the red one, this to be considered to be a photon, then what is going to happen is that the transition of an electron from higher energy to a lower energy, the transition obviously must satisfy the law of conservation of momentum, because otherwise it won't be it would violate the basic tenets of the law. So from here what we can tell that it is reasonable to apply the equations of photon and energy and of its momentum to the corresponding electron. So what we are going to do is that I'm going to use the red black one, just pull it over here, and you see that from here what I can get is that I can definitely get omega, this value would be what? This would be equal to 2 pi v followed by the wavelength, that is the lambda, right? And we know that this one P is equal to h upon lambda. P is equal to h upon lambda. So now I would plug in my latex equation once more. Okay, let us see how it looks like. So it looks like this. Make it a little bit smaller for you. Yeah. Here it is. So this one obviously is what? This is the angular frequency. I rate it as AF. So this one is the angular frequency, and P, this one, this is the momentum, right? This is the momentum for electron, and h bar is what? It is the reduced Planck's constant. So in classical physics, we know that the total energy of a system is the sum of kinetic energy and the potential energy. So kinetic energy would be what? P square, P square by 2m. And then the potential energy would be what? Obviously U, kinetic plus potential. And this would be equal to E. So I can, let me put out in a clean way, this would be this equation. Right? So we get the total energy as kinetic plus potential. Clear up till now? Okay. We can also write this with a little bit of cleanliness and doing the left hand side and the right hand side as this one. Okay. So this one would be this one plus this one. Clear? Okay. So from here, if we do the calculations of both the sides of the equation, what we get is this. Right? So from here, we get into this. Now, with this equation in hand, right? With this equation in hand, if I substitute this equation in here, which is this one, let me go up a little bit. This would be this equation. If I substitute, okay, let me make a little bit smaller so that at one shot it is visible, right? Now what I'm going to do is that I'm going to substitute, sorry, this particular equation, I'm going to substitute it over here in this equation. So if I substitute this equation into this, what is going to come? This is going to come. Here it is. Let me make it a little bit bigger. Yeah. So this equation, what we are seeing finally, I mean to say this equation, this particular equation, this equation is what is called the famous one-dimensional time-independent Schrodinger equation for electrons. This one, as you can see, this is the one-dimensional famous Schrodinger equation. Sorry, one-dimensional time-independent. We have not taken the time, otherwise things will become more complicated, of Schrodinger equation. So what do we understand from here? What do we get from here? So I'd just like to quickly, kind of a revise with this mathematics. So with the Boltzmann constant with this same kind of a thing, what we got, okay, let me now a little bit remove this, it will be a little bit. So with the Boltzmann constant and other things, what we got is first one variable with the x, as you can see. Okay, I think it is better to show it over here, right? And then from there, what we came over here is that we taken a hypothetical de Broglie wavelength and taken a electron which is at a room temperature, so and so. Then we have taken a one-dimensional electron distribution function. Which is this one-dimensional electron distribution function? It is this one, right? This particular. Okay, now let me make it bigger, right? So I make this one. This one is the one-dimensional, I would say, a function. This particular, the blue one, this I highlighted, right? So at a particular time when the coordinate is between, as I told you here, x1 and x2, this one. So what happens is that the electron distribution function, this looks like a standing wave, which is this one, this blue one, okay? And the important feature of a standing wave is that the two terms are written as one term depends on the other term, which is the one is the x and other one is the t. Okay, so from here, just a second. Yeah. So from here again, what we do is that finally what we get is that this one of the terms depends on x and the other term depends on y. And from there, what we did is that we got the next equation, that is the classical electromagnetic equation, which is this particular equation, this classical electromagnetic equation, which we have then we have substitute this equation and divided it with the exponential, and then finally from there what we get is that the equation we get is the Einstein's equation, E equals to h omega and p equals to this one finally. And then after that part, what we got is this one, this part, right? The total energy. And when we substitute this, we finally get to this equation. This is a reduced form, but you can look into that. This is what we call is the one-dimensional time-independent Schrodinger equation for electrons. Now, from here, what is the basic idea that I mean to say, why I am telling all this? Because this mathematical equation actually shows the classical nature of the Schrodinger's equation. The classical nature of the Schrodinger's equation. That means what? Okay, let me now go back to my slides a little bit so that you can understand. Yeah. So I would add it to the stage. Right. So here you can see actually that quantum mechanics actually now has got two parts. One is that quantum mechanics inherits the deterministic idea of classical physics, and another is that quantum mechanics has a probabilistic idea of random motion of particles. If I take the deterministic part of classical physics, then it has got a matrix mechanics, where all this position, wavelength, all those things are quite clear. I mean to say, these things are quite easily understood. And if I take the right hand side, that is the probabilistic part, then what we get is what is called the wave mechanics. So what I'm trying to make it a point is that from deriving this time independent, Schrodinger equation, we can see that the wave function of Schrodinger equation is actually no longer explained by what is called the Copenhagen interpretation. And Copenhagen interpretation is basically just an abstract mathematical structure having nothing to do with the reality of the described system. So whatever the derivation that I showed you today is basically gives a straightforward connection between classical and quantum world. And the physical reality, as I have shown it is in the wave function, is basically the random movement of the particles as it is defined in the wave function. So let us move on to the next part of our lesson. That is, what are the elements of quantum field theory that we are actually aware about? So you see from here, what we get are these different parts. So first part is what we call the standard model, which is definitely a part of our lesson. That is, this is basically the standard model. And from there, yes, this is the standard model. And what we see further from that standard model is the next one, which you can see from here. That is the classical fields, because as I told you, classical fields, etc., actually does carry a lot of value. And this one is basically a kind of a, you can tell as that of a classical field theory. Then we have got path integral formulation, canonical quantization. Canonical quantization means uh, uh, quantization of classical electromagnetic fields, renormalization, and other theories like gauge theory, etc. So the basic idea is that these inventions and resulted in a remarkable insight into the fundamental nature, that is, everything in the universe is to be found made up of some few building basic blocks, which are the fundamental particles governed by four fundamental sources, and you know what are those sources are all about. Okay, so we go to the next part, that we try to understand that why do we need a standard model. And here you can see that classical field, which is basically a part of, I would say, the special relativity, which is basically a part of classical field theory, and quantum mechanics. These are trying to get united into what is called a quantum field theory. General relativity and quantum mechanics are still trying to get united in string theory, although string theory is still on the process. It has not yet been made. And electromagnetic strong and weak force, sorry, this should be model. I have written a standard model mode. So it is united into what is called a standard model. So what we are trying to do is that we are trying to unite all the forces of nature into a safe house, which is called the grand unified theory. And our entire quest for particle physics, or any kind of a physics which you call, is basically to get a unified field theory or a unified model. Okay. Now, I would like to explain you in very easy words. I will go into the mathematics also from time to time. As you can now understand that these lectures are totally different from my videos. Because you understand, in the videos it is not possible so much to explain on the mathematics part, because videos are meant for, I won't say for a generic people, but people really don't enjoy the mathematics. I have seen it through my 2 years of experience in YouTube, but doesn't matter. You cannot avoid physics without mathematics. So I think this is a very good platform where we can actually do, and you can put up a comment in this comment section also. What do you think, how these things are going and how we are improving? And how I would improve. Okay, so here is the standard model. It's a nice kind of a funny picture. So all the bricks and cars and tiger and elephant that they have. So all of this. So what we can say, that an elementary particle or a fundamental particle, that means which you cannot divide further. It's quite obvious. So the development of the standard model was actually driven by theoretical and experimental particle physicists alike. The standard models of which is basically required for in order to get a quantum field theory. Okay. Now this standard model, which can be further divided and subdivided into many other parts, I've tried to make it I would say, as simple as possible. I really don't want to confuse with further things. So here is some kind of a very basic idea of what is a standard model. So you get the standard model. I have elementary particles can be divided in two parts. That is, one is the fermion and another is the bosons. So the fermions, I will come to that part because fermions itself has got a lot of things to explain. Fermions actually have got something which are called quarks and antiquarks, and leptons and anti-leptons. Bosons, which are the heavier particles that then have a gauge boson and a scalar boson. And these quarks and antiquarks are actually divided into up, down, charm, strange, top, and bottom. Just a second, I will have a glass water, please. Just a second. So these things, I mean to say, this up, down, charm, strange, top, bottom. Again, these strange names, why they have come, it's a history. I mean to say, I'm not going into that. But part of the quantum chromodynamics again deals with this part. Okay. Fermions, if you take electron, neutron, neutrino, muon, as you see, there are a lot of researches nowadays are going on neutrino particles. And we have got gauge bosons, which are protons, W's, Z bosons, and 8 type of gluons, and scalar boson would be the Higgs boson, which has been lately discovered with further details. Okay. Now you see here the fermions and the bosons. So we will try to understand a little bit of interaction between these two particular standard model. So you see the fermions actually have 1, 2, 3, 4, 5. I will say there are other features. So let us discuss on this. So fermions, those we formulate or obey the Fermi-Dirac statistics. That means these are spin half particles, and they obey the Pauli exclusion principle. Now remember, because they obey the Pauli exclusion principle, only one fermion can occupy a particular quantum state. That means one after another, after another, after another, it cannot be done. Right? So if there are multiple fermions which have a same spatial, I would say, probability distribution, then at least one property of each fermion, such as either a spin or something else, must be different. So fermions are actually associated with matter. Matter in the sense, our entire body or whatever we are saying, that is basically a fermion. So I mean to say, fermions, you can say they are not very good friends. Let us remember in this way. So if multiple fermions have the same spatial probability distribution, or for easy way, you can say that they occupy the same space, then either a spin or some particle will automatically change, right? So, and what is the Pauli exclusion principle? It states that two or more identical particles with half integer, I mean to say fermions, cannot occupy the same quantum state or with a quantum system simultaneously. And remember, this has been actually defined by Paul Dirac. Okay. So they are the foundations of matter, because the entire body, you, me, the laptop, the entire thing, these are actually made up of fermions. So you see now we are basically dealing with very small things, fermions, bosons. And on the other hand, we have got general theory of relativity, which is quite huge. I mean to say it's a huge thing. Now here I ask you a question today. It is my, I mean to say, you can answer anything on the comment box. Do you really think that such small things like fermions and bosons and quarks can be united on a cosmological scale with such big things, which is the general theory of relativity? I mean to say, I'm asking you this question just to enter into a kind of a nice understanding, because some people say, yes, theory of everything is possible. Some people say, no, it is not possible. But you see that dimensions of these, of 10 to the power minus 15 or minus 17 or minus 20, where the forces are a little bit different. And we are dealing with cosmological scale with black holes and galaxies, which are predicted by general theory of relativity. This is actually this discrepancy, and it is huge in order to get into one into another. Anyway, so let us go back to our understanding. Now, bosons actually has been named by Paul Dirac after the commemoration of Satyendranath Bose. I've made a complete video on the life of Satyendranath Bose, standing on the house in front of the door of Satyendranath Bose in Calcutta. So you can go there. So he developed it actually with conjunction with Albert Einstein, and his theory characteristics are Bose-Einstein statistic, Bose-Einstein condensate, and a lot of things. So anyway, what we need to understand is that these are integer spins, 0, 1, 2, and so on. They do not obey the Pauli exclusion principle. What does that mean? That with the same spatial distribution, they can occupy multiple stages. These are the force carriers. That means between this and this, if there is any force which is acting, bosons are basically the force carriers, W and Z bosons and gluons. There are 5 elementary bosons and scalar bosons, spin 0, and vector bosons, spin 1. And these are actually the vector bosons are basically the force carriers, and the scalar bosons are basically the Higgs boson, named after Peter Higgs, which actually gives the mass, which actually provides the mass. So that is one part. Okay, now what we see is that further we divide the particle zoo, that we call it as quarks. So quark is, again, why it is named quark, I will come to that in a different way, is a type of an elementary particle, and it is a fundamental constituent of matter. That means fundamentally this is the thing. So quarks actually, they are composite. I mean to say, they combine each other to what is called a hadron. So I will come to that later. So first it is the fundamental constituent matter. Now they are actually spin-half particles. Now if it is a spin-half particle, definitely these would be belonging to the family of the fermions. Quarks combine to create hadron, and these hadrons are nothing but the most stable of which are protons and neutrons. You can say the entire atomic nuclei are made up of that. All commonly observed matter, whatever you see around, are made up of quarks, down quarks, and electrons, and they experience all the 4 forces of nature. That means strong, weak electromagnetism, and a part of gravity. Right? Okay, if I come to the leptons, then they are not affected by strong force. Right? They are not affected by strong force. Again, they are the spin-half particles, and they experience all the 3 fundamental forces. And examples are electrons, tauons, muons, and so on. So these are the only elementary particles in the standard model of particle physics to experience all the fundamental forces. What are those? Quarks. That means in the entire standard model that we define, whatever the things that are being mentioned, all of them, out of all this part, the quarks are only one which actually experiences the 4 fundamental forces, not any other particle. That is very important for us to remember, right? Okay. So electromagnetism, gravitation, strong and weak interaction are being experienced by quarks, but not by leptons or any other forces. So now we can further divide these leptons into electronic leptons, second generation, and muonic. Now, why are you calling them first and second generation? I will come to that part later. And the third generation are called tauic leptons. Okay, strange names, right? So this is what the standard model is all about. Now, it is not difficult if we understand the nature of the standard model. I mean to say, which one interacts with what is the nature, what is the characteristics of this and this, what is the mediating forces that are experiencing between them. You will see from the microscopic level, if you move to the macroscopic level, understanding the laws of nature and physics will be much easier. Obviously, because if you understand the basic laws of nature, basic underpinning forces, why I'm sitting on the chair, why I'm not falling down, why the specs is on my face, why it is not falling down, why it is not going inside so all these things. So I always feel that particle physics should be the basic of all physics. I mean, it's a schools, Taiwan, if I remember, Taiwan is one of the schools. I was talking to one of them in this meet that I went, is one of the schools which incorporates a little bit of particle physics at the basic level for the schools, but we do not. Anyway, that's a next issue. Okay, so we come to the next part, which are called gauge bosons. So they act as a force carrier for fermions. Now, this is a little bit complicated, but what I would like to suggest all of you is that, say, for example, if you can make, I mean to say, this is a request, while you're studying the part of particle physics, you can make it in this way. These are these, say for example, leptons. Then you can further make it into this and this. Then you draw another, and then the quarks, and then you further divide it into three parts. I mean to say, if you make a kind of this kind of a structure, then you write down these features as this one. You write down this feature as this. Then you take another particles, and then you make into three, four parts. I'm going to say this would become a little bit easier if you divide it hierarchically. And you will see most of the books, they actually frame it in this way. I mean to say, they divide it in a hierarchy. So it is wonderful that while you're reading, say for example, this earlier slide, if I go back to this, fermions spin up this. Bosons, you make it into this way. So for example, if I make this one as fermion and then into gauge bosons, then you further divide this and you write down the characteristics. This one as second and then as third. I mean to say, if you create a kind of a figure like this kind of a figure, I think retaining and memorization, reading those things will be much more easier, rather than just mentioning on the features, etc. Right. Okay. So we go to the next one, which is the gauge bosons. They act as a force. So fermions are here. Remember, where are the fermions? This one. Elementary particles. First is the fermion. Fermions have got Fermi-Dirac statistics, etc. Then we have got quarks. Okay, let us skip quark. I am now coming to the gauge boson, which is acting as a force carrier between fermions. So if one fermion it is jiggling in between, it has got. So photons, part of the fermion, W and Z bosons, gluons are gauge bosons. So you can really make into this 1 to 3 way, right? Gauge bosons obviously have spin 1. Again, you see, because where we are, so bosons, because it is here spin 1, so obviously gauge bosons will have spin 1. So it follows very sequentially. Gauge bosons are force carriers, obviously. Scalar bosons, I would say, these have actually spins which is equal 0. So a boson is a particle, I would say, we will come to that later, whose wave function is symmetric. Obviously, the wave function is symmetric under any kind of a particle exchange, which we will later examine in Feynman diagram. And that is why they follow the Bose-Einstein statistic, because its wave function, remember, it is symmetric. Now, there is something which is called a spin statistics. I'm not covering it in this lesson, which tells that all bosons have an integer valued spin. Scalar bosons are basically the subset of bosons with 0 valued spin. So the name scalar boson, as you can see, arises basically from quantum field theory, which tells that fields of spin 0 particles transform like a scalar under Lorentz transformation. This is very important. Okay, let me put it in this way. Just a second. These are the points which are very important. I would request you, does it copy and paste over here? Yeah. Right from my notes, right? So remember this one. These name scalar bosons actually is coming from definitely quantum field theory, which demands that fields of spin 0 particles, this is important, fields of spin 0 particles transform like a scalar under Lorentz transformation. That means they are Lorentz invariant. Okay, I will plug in one thing also from my notes. This one, remember, scalar boson is a boson whose spin value is 0. Oh, I'm so sorry. I'm not being able to share the screen. So sorry. Yeah, here you go. The scalar boson is a boson whose value is spin equals 0. A boson is a particle whose wave function is symmetric under exchange, I mean to say particle exchange, and hereby it follows the Bose-Einstein statistics, most importantly, and this one. Here you see. Sorry. Yep. A boson is a kind of a boson is a particle whose wave function is symmetric under particle exchange. So it actually would go in a different direction. First is this point. This is number 1. Sorry. This would be number 1. This would be number 2. And this would be number 3. Okay. Scalar boson is a boson whose spin equals 0. That is fine. A boson is a particle whose wave function, that means if I take any kind of a wave function, x and t, this would be symmetric under transfer. So if I take it as S, right, whose wave function is symmetric under particle exchange. So here is a particle and here is a particle. If it is exchanging the particle and then it gives a virtual photon, whatever be it, and therefore follows the Bose-Einstein statistics. It is following the Bose-Einstein statistics because the wave function, this one, is symmetric. The spin statistics theorem, whatever. Now you see what I'm trying to tell, this part. The name scalar bosons arises from quantum field theory, which demands that the fields of spin zero particles transform like scalar under Lorentz transformation. So we will all know about special relativity, that is Lorentz invariant. Now I would like to tell you something very important. So here you can see right at this moment, quantum field theory and special theory of relativity in some way are coming to join their hands mutually with each other. Can you see this one? Why? Let me show you again. Read this line again. Let me again make it in a fresh way. Just wait, I will plug in one by one. First, number one is this. A scalar boson is one which has got a spin value which is equal to 0, right? Then we see a boson is a particle whose wave function is symmetric under any kind of a particle exchange. This is point number 2. And this is where the special theory of relativity comes around. I'm just plugging it from my notes so that it is visible to you, right? So part number 1 is this feature. Second is that a boson is whose wave function is symmetric. Symmetric means whatever it happens, it is invariant, kind of a, you can say in general relativity what we talk about tensor. And the name scalar boson, this is the which demands that fields of the transform like a scalar under Lorentz transformation. Transform like a scalar under Lorentz transformation. This is very, very important. I hope you can take the notes. Now, Lorentz transformation is where? Obviously, it is a special theory of relativity. And that is why now we can say here, from here, what we can see and what we can deduce from this 1, 2, and 3. So this is 1, point number 2, and point number 3. What we can see is that you see here special relativity, STR. Before that, obviously, we have got classical physics, CP. The STR is this one, the Lorentz transformation, and get unified into quantum mechanics, which actually results into what we called as this one, quantum field theory, right? So we have got the classical physics, we have got the Lorentz transformations, special theory of relativity, and where we are applying? We are applying at the wave function, that is these quantum mechanics wave function with 2 variables, and what we are getting is what we call quantum field theory. Isn't it beautiful? We have just shown the Schrödinger's equation, which is a limitation in terms of classical theory. We have earlier shown that spontaneous emission cannot be described by Schrödinger equation, and today we have shown actually the reason of the limitation, that the radius of that spherical mass, this one, those who have seen it, I think you can just quickly, let me show this one. If I go back, yep, this part, yep. Here we can see that the RE, this one, was going towards infinity. And then that is why it is unable to describe. Then what we saw is this one, that the Schrödinger equations ultimately leads to this one, this particular part, which is basically the classical time-independent one-dimensional Schrödinger equation. And now what we see? We see that the standard model, we have seen the standard model, and what we have also seen over here is that the 3 important features of scalar boson and how it follows the spin equals 0 because of the symmetric nature of the wave function, and it follows the rules of special theory of relativity, that is what is called the Lorentz transformation, and hence it becomes something which is called an invariant nature. So this is something which is the standard model. As you can see here, I have tried to explain it with simple idea that the matter actually compares any matter. Say, for example, a car consists of quarks and leptons. Quarks are further divided into hadrons. Hadrons have again two parts, mesons and baryons. Baryons actually comprises of the nuclei of atoms of the molecules and matter, and the force carrier are gluons, the WZ and Z bosons, the photons and the gravitons. Gluons are basically mediated by strong force, uh, and these strong force, what do they do? They bind quarks together and they form the hadrons. So gluons trying to bind the force and forming the quarks together and forming the hadrons, and hadrons are basically what? Quarks, and quarks are basically what? The constituent of matter. So you can really if you want to write it in this way, even you can do that. I think that would be really wonderful. Okay, so here we get what is called are the quarks. Okay, I mean to say it is really fun if you can make it in that way. So these are actually the quarks. Say, for example, the Q1, right? They are basically forming the hadrons. They are basically forming the hadrons. So quarks are basically matter. That means you and me and everything, right? And hadrons are formed by mesons and baryons and so on, as you can see over here. Now here we have got something which is called a gluon, which is a strong force. Now gluons are doing what? They are basically forming the strong force, SF. These strong forces are, if these are the, small quarks which are binding the nucleus together. They are binding the quarks together. And they are actually forming, then again, these are going back and forming the hadron. And hadrons are forming the quarks, and the quarks are forming us. For example, this is me, Shaunak. Okay, so quarks are going back and forming the matter. So it is a very sequential from here to here to here, and the gluons holding the forces and going back to hadrons, and they are forming the matter. I mean to say, this is how things actually happen. And as you can see, the W and Z bosons are actually the weak force, photons are the electromagnetic force, and gravitons are the gravity. Okay, it is already quite a long session today. So, but this standard model has got a lot of problems, I can tell you. These problems, there are certain limitations of the standard model. What are the limitations that we are going to discuss today? I will be a little bit late to log in. I will try to log in by say 9 or 9:30ish tomorrow. And what we are going to learn tomorrow is that what are the limitations of standard model, why there are limitations, and how these limitations create a kind of a, I wouldn't say problem, but it creates a kind of a, I would say, areas of further study and research into particle or theoretical physics. So that's all for today's video. I think you have liked it. I would really wait for those who have been watching. I see very few, but those who are constantly watching for 58 minutes and few seconds going on, please do put in your comment how these things are going, because I really cannot see any comment coming up. So I really don't know how things are going, whether you're enjoying, is it too difficult, or the mathematics needs to be a little bit easier, etc. So tomorrow the agenda would be understanding the limitations of standard model, and then we will go back to the fundamental interaction. This part will take 1 or 2 more classes, and then we will start going into the complex equations of, I would say, quantum field theory, but I will make these complex things very, very easy for you. So that's it. Thank you very much. I will be back tomorrow to trying to explain the limitations of standard model, what are the things, etc., which are going on. And as you know that on 19th, Professor Abhirup Datta, head of astronomy from IIT Indore, is coming up. I've got another surprise on you for 26th of November, which I'm going to explain soon through the videos, etc. So that's it. Thank you very much. And do let me know in the comment box how things are going. Goodbye.